Hello guys and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we have an excellent problem, in my humble opinion, around this idea of acceleration, velocity, distance, distance change with time, and all those dynamic principles from mechanical Newtonian laws. And here, this is about escape velocity. It's a very straightforward problem, and it's a great one too, in my opinion, because it relates everything we've been talking about, everything you've learned, with things that are useful and that just, you're able to solve already, just with the knowledge you have. So without further ado, here's a problem statement. The acceleration due to gravity of a particle falling towards the Earth is A equals minus g r squared over r squared, lowercase r, where lowercase r is the distance from the center of the Earth to the particle, r is the radius of the Earth, and g is the acceleration due to gravity at the surface of the Earth. So if the radius is 3,960 miles, calculate the escape velocity, that is, the minimum velocity with which a particle must be projected vertically upwards from the surface of the Earth if it is not to return to the Earth. As a hint, velocity 0 for r infinite. So really, in my opinion, the hardest thing here in this problem is having this understanding. They give it as a hint, so the hardest thing, we already are over it. Because the idea here is, if you are to go anywhere, if you are to launch yourself upwards and your velocity is 0 anywhere before you escape, then gravity is going to pull you back, right? So just like jumping, anything that goes up must come down. However, if you have a velocity that's able to escape completely this force field around Earth, right, due to its gravity, then when you get to this point, Earth is not going to be able to pull you back anymore, and therefore you will have escaped its gravitational field force. Okay, so the first thing I'm going to do is I'm going to convert this number from miles into meters, because I'm not crazy. And so therefore 3,960 miles, I'm going to go ahead and convert that. It's going to be approximately 6.373 times 10 to the 6 meters. So I can work with SI units. And the next thing is I'm going to note is that the equation that we're given has two constants and one variable. These two guys are constants, the radius of the Earth and the gravitational force, and this is a variable, and there's a square here. And this is a variable, okay? Note that we have an equation relating acceleration and distance. And if we were to use just the basic principles of dv dt and how v is equal to dx dt, we are always introducing the variable time into this. But we don't have time here, and we don't really want to include it because all we're dealing here with is distances and velocities and accelerations. So therefore, there's a neat trick that we can do, which is where I'm just going to rearrange this equation and say, okay, then if this is true, this means that dx divided by v equals dt, right? And if this is true, I'm going to then substitute into this equation, and then I'm going to end up with, okay, so therefore acceleration is dv divided by dx divided by v, which is the same thing as dx with v multiplying up top there. And if I do it this way, now note that now I have an equation that relates only acceleration, velocity, and distance, right? Travel in any direction that I want. In our case, the distance traveled, the x, right, is being called r. Instead of x, I'm going to have r. So really this, I can write, and no, this is exactly the same thing. I'm not changing anything whatsoever here. Just saying the rate at which velocity changes with r, the distance r, instead of the distance x, times velocity. And then I can take advantage of this to be able to calculate my escape velocity, which is what the problem is asking us to do. Okay, so I'm going to go ahead and copy this over here. I'm going to note that acceleration has to be equal to this, and acceleration also has to be equal to this. So therefore, this equals dv divided by dr v. And now I have an equation in which my unknowns are r and v, and I can solve it. I can solve it with that hint that was given to us, which is as my r goes to infinity, my velocity goes to 0. Or when my velocity reaches infinity, my r is going to be infinite because r doesn't mean anything anymore because Earth cannot pull us back or this particle back. Okay, so what we can do here is I'm going to rearrange. I'm going to let's leave the dv v on one side, and then I'm going to set everything else to the other side. So I'm going to have minus g r2 squared r squared vr, and I can here integrate for these two sides. And here on this side, I'm going to go from v naught, initial velocity, or the escape velocity that we're looking for, all the way to a given v. Okay, I'm not going to substitute just yet. And over here, I'm going to start at a certain point, and then I'm going to end at a certain r. Which point is this? If I'm at the surface of Earth, I'm not starting at 0, right? But rather, I'm starting at r. Right? And if we go back to the simple drawing we have here, we are starting here. We're not starting here. So therefore, it's from 0, it's from a distance r, if this is my center here, right? So I'm starting from r when my velocity is 0. My velocity is v naught. Okay, so this integral here is going to give me v2 squared minus v naught squared divided by 2. And here on the right side, I'm going to have, this is a constant, so these guys leave the integral. And I'm going to have the integral of r squared dividing r squared. So that's going to be the same thing as r minus 2. And you guys know this is just plus 1, so this is going to be r minus 1 divided by minus 1. Okay, so that means that this is going to be minus 1 over r, or let's just do this, over r, as we go from r to any r that we want, uppercase r to any r that we want. And now if that's true, then I'm going to go ahead and say v2 minus v naught squared divided by 2 equals minus g r, or g. And then this becomes 1 minus 1 negative r, and then minus negative, so positive 1 over uppercase r. Brilliant. Oh, there's a square here that I forgot. All right, cool. Did I forget it? Oh, still. Okay, cool. So now I can go ahead and start. Now I'm going to go ahead and send this negative here inside, this negative here. So what I'm going to do here is I'm going to get rid of that negative, and this is going to be positive. It's going to become a negative, just like that. And with magic of tablets, I've skipped one line of the equation. Okay, cool. So now the other thing I'm going to do is send this to the multiply on the other side, like so. Brilliant. And now I am ready to do some substitutions. What I'm going to do is I'm going to note that my velocity tending to 0 is related to my r tending to infinity. And I'm going to do both these things here. So this guy here is going to tend to 0, so that's going to become 0. This is going to be just the negative of the escape velocity squared. And over here, and note that this is only true because I want to find out what's the escape velocity, right? This is not like a given. This is something I'm forcefully putting in here to be able to find escape velocity. So in other words, it's not that the equation that I'm about to find out is always true. This is only true if I'm tending to v0 with r going to infinity. Okay. And then here on this side here, I'm going to get 2g r squared. And note that as this guy here goes to infinity, this whole term here goes to 0. Right? So this whole term goes to 0. And I'm only going to be left with this term over here. And therefore, that's going to be times negative 1 over r. Boom. Okay, cool. What next? Squared r, negative, negative. Therefore, v naught equals the square root of 2g radius of r, uppercase r. Just like that. we just transform something that sounds super complicated into something that's super simple and, by the way, accurate. Okay, so now if I want to know what's the escape velocity that I need, V naught or VE for escape velocity, that will be just 2 times 9.81 meters per second squared times the radius of Earth, which we converted to 6.737 times 10 to the 6th. And this turns out to be about 11.180 something, 182. We're going to do approximately 11.2, and this is in times 10 to the 3rd, because this is to the 6th, then it becomes the 3rd, and that is meters per second. Or, if you want, it's the same thing as 11.2 kilometers per second. Okay, not per hour. Cool, and let's just make sure this makes sense in terms of the units. What we have there is the square root of 2, which has no units, then we're going to multiply meters per second squared, and multiply that by meters. So we get the square root of meters squared second squared, which is meters per second. So it does make sense, it checks out. Cool. All right, that's our answer right there. So if you want to escape Earth, start training that speed, because you need 11.2 kilometers per second to be able to escape the gravitational force of the Earth. I hope this was useful. Again, I really like this problem. I think it's not only, practical, but meaningful. And, we can solve it just by using the knowledge that you've gained here so far. And if this was useful, consider giving this video a like. If you have any questions, just leave them below in the comment section, and I'll try to address them. And we'll talk soon.